When you're calculating directional derivatives, just like the examples we saw in the previous video, it's actually really useful to use a more compact notation. So let's have a look at that. You can find this in section 10.6 in your lecture notes. And this is really about notation. We've seen so far that we would write a directional derivative of a function x, y, z as something that is quite long. You're calculating the partial derivative at point x, y, z. You're multiplying by the component of the unit vector. Remember, unit vector having components a, b, and c. And then you're doing the same for y, x, y, z, b plus fz, x, y, z, and then c. And the great news is that there's various ways that you can make this way more compact, so that when you're writing, you don't need to spend billions of years just writing down the definition of things. A simple way to write this is actually just in terms of components in a vector form. So you can write this as fx, fy, fz with the dot product a, b, c. If you don't know or don't remember dot product, the way to calculate it is simply the dot product of two vectors with a dot is the same as the modulus or magnitude of each times the cos of the angle that they're doing in between them. The other way to write this is simply as a, b cos theta. Now, because this is a dot product of two vectors, we already know which vector this is. This is the unit vector. What we can have a look at is what this vector is. And this is called the gradient of f. The gradient of f is usually written as something like grad f. And it is written with a symbol. Sometimes you'll find a specific vector notation. In Physics 101, I will not use it. And typically in LaTeX or in computer language, you'll see that this is also kind of bold. But because there is no confusion with anything else, this is always a vector. It's the gradient of f. And in 3 dimension, it has components fx, fy, fz, with these being the partial derivatives. As a vector, you can also write that the gradient of f is given as fx, y, fy, j, fz, k. This is what it means. This is really useful because we can get rid of this long way of writing and actually write it like a pro. That the directional derivative at a point x, y, z for this function, for this unit vector, is simply given by the dot product of the gradient of f with the unit vector. Way more compact and definitely like a pro. If you think this is still a lot to write, there's good news. You can further simplify it, and specifically because many times what we'll write is du f of this capital X to mean something that will not depend on a specific number of dimensions. For this case, this x would be the same as writing x, y, z. But it also means that this notation will be valid regardless of the number of dimensions or variables that f depends on, and it is incredibly compact. I would definitely encourage you to use this notation and try to go through the examples you find in the lecture notes in section 10.6. Make sure that you can get to the final answers and that you understand everything about it. In some problems, you'll be told to calculate a directional derivative at point capital X and then a coordinate. This is what it means. If you're told to calculate this this is just the same as a directional derivative. And of course, if you become a pro, when you're calculating a directional derivative, you could calculate the components of the gradient vector of f directly and then calculate the dot product. What you really need now is practice. That's also what I need for the ukulele. So while I practice a little bit more on the ukulele, make sure you attempt the examples, and I'll see you in the next video.